All right, so we're going to call this relationship, like I said, we have a relationship between concentration and rate of reaction, okay? Where we're saying as concentrations are going to go up, rate's going to get faster. Makes sense to us. So we'll call this relationship between reaction rate and concentrations. The rate law or rate equation is how you might also see me ask for it on an assignment. And so if you have A and B and they collide, and then when they hit, and again, sort of it gets much more complicated when you think about, okay, there's both sort of this probability that they'll actually have a collision, and then there's also an orientation that they need to be in for this to be successful, but we're sort of way oversimplifying it. They form C. And so the rate of this is going to be equal to our proportionality constant, our rate constant K, times the concentration of A, times the concentration of B. Okay? And we could also set this all equal to the disappearance of A. This also needs to be equal to the disappearance of B. This needs to be equal to the appearance of C. I just want to sort of alert you to figuring out, what information do you have, what things can you set equal to figure out what you might be being asked for. Okay. So we're going to talk about rate laws and then also something called reaction order. And reaction order is related to something called molecularity, and we'll go through some slides on this as well that hopefully improve what I'm about to draw. And this is related to the number of collision partners. So the number of actual molecules that have to physically collide to make product, okay? So here in this case, A and B react to make C. You may need 2 molecules of A and 1 molecule of B to make whatever your final product is. Maybe you need 4 things, who knows, okay? So just when we're talking about molecularity, we're talking about literally the number of molecules that need to collide with each other to make product. Okay. So we can have what we would call a first order reaction, okay? So we can write this as just A turning into C. Our rate law would be, we have dA dt is equal to negative K, the concentration of A. In this case, I've just moved the negative to the other side, and the reason for doing this is we're going to, by convention, always let rate constants be positive, okay? So the K value will always be positive no matter what. So let's talk about units for a second. What do the units of reaction rate need to be? What are the units of concentration? Molar, moles per liter, okay? And I think earlier I drew time, but I gave it a unit that we like to use, seconds, okay? So molar per second would be our units for rate, okay? So given this sort of first order information here, what are the units of K, my rate constant? This is molar per second, this is molar. It's 1 over seconds, or seconds to the negative 1, okay? Has to be the unit. So pay attention to the units, keep track of the units. One of the things that will be a hint if you're shown rate constants and then you're asked, is this a first order reaction, second, third, 0? One way to decide would just be to look at the units. The end. I can make a decision, okay? because they're going to change depending on reaction order. So for a second order reaction, we could have A plus B forming C. Okay. So again, we have dA dt has to be equal to, we have to have the dB dt is changing, and so we can set this all equal to negative some rate constant, concentration of A, concentration of B. So what are the units for the rate constant for a second order reaction? This is molar, this is molar. We need it to be molar over seconds. Okay, so what are the units? Such that I can get molar over seconds on the left side of my equation, and I have right now molar squared on the top of the right side of my equation.
1 over molar times seconds.
I love it. Thank you, Paul. 1 over molar times seconds. Okay. So for a third order reaction, okay, maybe I have A and another molecule of A and a molecule of B, and they all collide and form C. Okay. I just want to warn you about your book. It's going to write things like this, where the 2 may actually be a stoichiometric coefficient. And it's also going to write things like this, where this is meant to represent A plus B, but is not necessarily a stoichiometric coefficient. So just careful as you, just pay attention to the information given to you. And so ideally, go slow, read what you have. Okay, so 1/2 dA dt equal to dB dt. Again, this is in your book, it's written like this, and this clearly suggests that it's a stoichiometric coefficient, but it doesn't actually want it to be. And we'll talk about that as we keep going. Yes? So this is the idea of, again, this molecularity, this number of things that have to react in order to make product. There's a nice example that hopefully I'll get to, and it'll clear some things up, where fluorine is reacting with some chlorine dioxide, and we have to have, for the purpose of balancing the equation, in that case, 2 chlorine dioxide molecules for stoichiometry, but you'll see it also makes 2 of the product. And so actually you only need 1 each of those 2 things reacting to each other to make product. So your reaction order is going to be 1s, even though stoichiometry is 2. Let me get to that slide, and then let me know if it gets clearer when we have an example for it. Okay? So we can write this as negative K. We have the concentration of A, the concentration of A, the concentration of B, and you can write this then as negative Ka squared B, okay? So this 2 here, like I said, it in this case sort of happens to be the same as a stoichiometric coefficient if you need sort of 2A plus B to balance your reaction, then that 2 there happens to be the same as the stoichiometry of your reaction. It does not have to be. You might have a balanced reaction where your stoichiometric coefficient is a 2, and the reaction order, okay? So there's no superscripts up here, they're all 1. I'll write the generic form in a second. reaction order does not have to be the same as stoichiometry. So this was sort of, I think the book also calls this unimolecular. This would be bimolecular. This is called termolecular. A couple of things. So for convention, I said let K always be positive. So always let your rate constant be a positive number. Okay. For this here, I need meters per second, meters. I need molar per second. I have molar, molar, molar. What are the units of this rate constant have to be? Beautiful. 1 over molar squared times seconds. So for a generic nth order reaction, the units for your rate constant would be given by molar to the 1 minus n seconds to the -1. Okay. So for second order, 1 minus 2 would put a 1 molar in the bottom. 1 minus 3 for third order would put molar squared in the bottom. Okay. So sort of a generic way to write your rate law and identify what reaction order you're dealing with. Rate is equal to K. This is, of course, just now for a two reactant example, but you could have more. K is your rate constant. X and Y are determined experimentally. Okay, like I said, we'll go through an example that will hopefully help clear this up. They do not equal stoichiometric coefficients. They can be fractions. Stoichiometric coefficients, we said we're going to go ahead and always just make them whole numbers, make it easy for me. X and Y don't have to be. You have to run a reaction to get this information. Okay, so you would have to hold the concentration of one of your reactants constant and vary the concentration of the other one and measure the rate at which you're getting product. And then switch it. Hold the other reactant constant, vary the concentration of your first one, look at what's happening to the overall formation of the product. Okay. X here is called the reaction order with respect to reactant A. Okay. This is reaction order with respect to B. They don't have to be the same number. And to get your overall reaction order, you add them up. Plus, if you had more, whatever it might be. If you have more reactants involved. Okay. And so for this case here, this is a second order reaction because the reaction order with respect to A is 1. The reaction order with respect to B is 1. 1 plus 1 is 2. This is just 1. I only have A involved.